So once again, we want to say good evening to everybody and welcome to our webinar, taking a look at the top events of 2021. I am Joe Deli Carpini, the Science and Operations Officer, and helping me out tonight, Rodney Chai and Bill Leatham, two of our fine meteorologists, who I'm sure you're familiar with from other presentations. So we're going to all take a piece of the puzzle here and walk you through some of the top events of 2021. And to start, we're going to have Rodney, because he's our winter weather nut and guru. He's going to start with some of the winter storms and take us up through, I believe, the summer. And then Bill will take it from there, looking at some severe weather and tropical weather. And I'll finish it up with a look at some of the end of the year weather. So Rodney, I will hand it over to you to start with our February 1st and 2nd major winter storm. Oop, did we lose Rodney?
I can't hear him. I don't know if is he on mute?
Let's see. Rodney, you're not on mute. I can see you're unmuted. Let's try it again.
You guys hear me now?
There we go. Good. All right, Rodney, go ahead and take it away.
How about this?
Yeah.
Okay, thank you. Thank you, Joe. And
no problem.
Sorry for the inconvenience, everyone. So, yeah, it was kind of a backloaded winter where we had quite a few major winter storms, actually, February, March, and April. And we'll begin with this one, February 1st to 2nd. You can see, this winter storm dropped over close to 3 feet of snow in parts of Pennsylvania into New York State. And for our area, it's not too shabby. We had up to 2 feet of snow. But for southern New England, the key takeaway from this storm was the sharp snowfall gradient, as we would take a closer look in the upcoming slides. So check out the tweet by Harvey Leonard on the right-hand side. You can see, Logan Airport 1.2 inches, but just 10 miles inland, you're getting over a foot of snow to 18 inches. So, and then on the left-hand side, you can see the contrast between one side of Topsfield and another side of Topsfield. It's just night and day difference. And so the thing is that for a lot of us who live kind of on the coastal plain in eastern Massachusetts, snow was falling, and in this case you can see it's falling at a good clip. But it was being in early February, the sun angle is a little bit higher, and the temperature, since it's 33 degrees, just above freezing, it had a hard time accumulating. And at Logan, you can see that the temperature actually never dropped below 33 degrees. And that's kind of a red flag for forecasters. And so even while, it is snowing steadily, you can see all the light snow in the weather observation, it had a hard time accumulating on surfaces due to melting. And again, to some extent, the early February sun angle. So taking a look at the synoptics, the surface map, it was a nor'easter, but pay attention to the track of the center of low pressure, because it would have some implications on the slides that I'm going to talk about in a little bit. And notice how it is kind of like a broad low pressure system, and it's taking its time, to eject out the New Jersey coast and pretty much goes parallel to Long Island. And and as a result, there's the surprise impact on the south coast. There was significant beach erosion and inundation observed on Martha's Vineyard. And, also in westerly Rhode Island. So typically, we do not expect inundation or damage due to wave action along the south coast, especially with northeast winds. If you think about the geography, it's kind of surprising. But there were several factors at play. So the effect of the persistent southeast winds, so as I alluded to earlier, this low pressure system was taking its sweet time ejecting from the New Jersey coast, and as a result, southeast winds persisted longer than what we typically see from a coastal storm, and the seas were able to build to above 20 feet from the southeast with wave energy focused on south-facing shorelines. So the key takeaway, for forecasters is that if you see a storm south of New England exiting slowly to the northeast, it can generate pretty large southeast swells and storm surge. So you have to keep an eye on the south-facing coastline. So, a few days later, we have this, again, another nor'easter, but this time round, it was known for its heavy snow band. Some of you might remember, some of you who missed out on the snow a few days earlier, you had, at some point, 3 inches per hour snowfall rate, and you can see it's actually kind of line up right along the I-95 corridor. So it was kind of a high impact event for that part of the area. And so this was the radar. You can see, pretty impressive to see those yellow color reflectivity showing up on a winter storm. That is really indicative of very heavy snowfall rate. And you can also see a secondary band over Nantucket. But the main band was really centered from northern Rhode Island into Metro Boston. And there were reports of, in this case, that was actually the report by Joe, who lives in Norwood, and he reported 3.6 inches of snow in the past hour, and that's just amazing. 3 to 4 inches per hour snowfall rate within that band.
And Rodney, I remember you were very jealous when I sent you a message about that. So.
Yeah, I was jealous, but I'm happy you got it. But so looking at the dynamics of what led to this heavy snow band, we looked up to 10,000 feet above the atmosphere, and it is something. It's a term, frontogenesis. Basically, it's the lift caused by a difference in temperature, much like a front. And you can see that the band kind of extending from Long Island into southeast Massachusetts, and then that was on Sunday afternoon. And notice how the purple lines were kind of, that's indicative of a very impressive frontogenesis at 10,000 feet. And typically, you would see heavy snow bands setting up just north and west of that, where you have the frontogenesis. So in this case, unsurprisingly, it's over the I-95 corridor. And coming down to 2,500 feet, and this is taking a look at the temperature contour lines. And so basically, you can see a pretty sharp temperature gradient set up just southeast of southern New England. And typically, when you see such a tight thermal gradient, you result in strong lift just to the northwest. And in this case, that explains the secondary bend over Nantucket as well. And moving on to March. So we had March, the first 2 days of March was pretty cold, and we had an Arctic blast and along with it high winds as well. So taking a look at some of the peak wind gusts across the area, like Worcester, 62 miles per hour, Norwood, almost 50, Provincetown, 56, so pretty impressive wind along with the Arctic front. And what led to this Arctic outbreak and high wind event? So notice that you have at 18,000 feet, you have this closed low feature over Ontario, and notice the strong winds, around it. So those are, when you see the flag signal, that's 50 knot wind, and then every dash line that adds 10 knots to it. So you're basically 70 to 80 knot wind around the close low. So this implies very cold air moving into the region with strong winds aloft. And when those winds mix down, you led to those gusts that you saw, 50 to 60 mile per hour gusts, and alongside with very cold temperatures for early March. And so, the temperatures were in the teens and over 20s, and with, winds gusting up to as high as 40 to 45 knots. That's how you get the sub-zero wind chill. And there we go, the current wind chill, widespread negative wind chill values as a result of the cold temperatures and high winds. And going to April, so this was mid-April. Again, this is high elevation snowstorm because that late into the season you need the higher elevation tends to do better because of the marginal temperatures, and up to a foot of snow fell in the hills of Massachusetts and Connecticut, including a foot of snow on top of Mount Wachusett at 1,800 feet. And then the Connecticut hills did pretty good as well. Widespread, I would say 4 to 8 inches at around 500 to 1,000 feet. And taking a look at the satellite picture, you can see, kind of make out like an eye, the eye of the center of the low pressure system. And Eric Fisher took this picture, and he was kind of in the eye of the storm, and he saw blue skies on the Cape. And then taking a look at the surface map on the left-hand side, you can see the strong low pressure system was located near Nantucket. And because of the sheer intensity of the system, sometimes you can get thunder snow, and that's and you can actually see the signature of thunder snow on radar on the left-hand side. That's actually a depolarization streak, and it's when you see that signature, that's a precursor for lightning. And you can see that this is actually one of the satellite products that you can play with. So in this case, it indicates a lightning strike in Metro West, and some of you did actually report thunder snow in that neck of the woods. So what is a depolarization streak? It occurs when ice crystals above melting level becomes electrified and vertically aligned, and and then you will be able to capture this on the differential reflectivity product on radar. Basically, typically negative values to 0. And April 21st, again, backloaded winter. So not only do we have snow, we also have severe thunderstorms as well. So on the left-hand side, you can see all the wind reports in blue from mid-Atlantic states to southern New England. You can see that line of storms moving through southern New England. And then on the back side of it, that is snow. And, snow was reported in the higher elevation, in the Berkshires and the East Slopes. And so not only did we have damaging straight line winds, we actually also had a tornado as well. Not in our area, but just outside of the area that we forecast for. And this is actually, I believe, New York City forecast office area. And this is the Connecticut tornado. Ef-0, it didn't travel much. It was 1 mile, but there was a tornado on the ground, and it was the earliest tornado on record, for Connecticut, because the previous record was April 26th. And, Ryan Hanrahan tweeted out, pretty sure it was the first time in Connecticut we have had a tornado warning followed by snow 3 hours later. So that's a pretty wild day. And taking a look at the surface ops that day, what really jumps out in the surface map on the right-hand side is that, look, notice the warm front backing. And, when you have such a setup and with the, sufficient moisture, in this case, you have dew points near 50 degrees, not impressive, but impressive for April. And when you have a warm front backing like this, you have to be cautious as a forecaster, as a radar operator. You have to be on the lookout for rotating storms, and that was actually what happened in Western Connecticut. You had a storm that was able to have some spin to it, and it was close to the ground, and that dropped a very brief tornado. And taking a look at some of the meso-analysis products, the 0 to 3 kilometer helicity or low-level spin. Notice the high values in the northeast as a result of the strong jet stream wind. And the other tool that we like to use is, being so early in the season, the dew points are relatively low. You're not going to get a whole lot of surface-based instability. So you want to look at the 0 to 3 kilometer instability of Cape and overlay it with the spin. So areas that kind of overlap, that is kind of the area you have to be on the lookout for, like, you know, a rotating storm. And at this point, I will pass it over to Bill, who's going to talk about tropical weather.
All right, thank you very much, Rodney. This was actually a pretty busy July for us and across southern New England. So from Tropical Storm Elsa, the main impacts that we saw from it were heavy rainfall, but there were some gusty winds at times, and you can see a nice picture from, it looks like the space station of Elsa. So if you want to go to the next slide. Here's just a quick list of the peak wind gusts from the storm. Again, the real highlight, and you'll see in a second here, were the heavy rainfall and the flooding that we got from it. But we did have some strong wind gusts out of it. Most locations saw anywhere from 45 to 55 miles an hour, with the highest gusts around 67 miles per hour. And the duration of this was relatively short, so because of that, we really didn't get a ton of damage from the winds that we saw from the system. So you can see here just a quick image of the amount of rain that we received, and as is typical with tropical systems, as they get up into our area, usually to the left of the track, or the western side of the track, is where the heaviest rainfall is, and typically, if you kind of had an idea of those wind gusts, on the eastern side of the storm is usually where you have the strongest wind gusts. But you can see on the western side of the track, we had anywhere from 2 to roughly 5 inches of rainfall, depending on where you were located across southern New England. And then, so here's just an image of one of the areas that got a pretty good amount of rain. The Willimantic River, you could see, you could see the water going across. And then here's some more images of some urban flooding out of the Worcester area. So you can see, obviously, the water level is pretty high with the system, or due to the system. And then, as the storm got out of our area, we have to give homage to Rodney because he really loves the snow. As the storm exited and went up towards Greenland, the Greenland area, at this point, it wasn't a tropical system, but had been giving some snowfall to Greenland. So moving on into the middle of July, we had flash flooding in Somers, Connecticut, and an Ef-0 tornado. One thing you're going to see come up here with several of these tornado cases is that there's always usually a boundary that is kind of the area where the storms are developing. But in this case also, that boundary helped produce an area of very heavy rainfall. And you could see on the images below, you can see some of the images of the tornado. You can see the road that's washed out due to that, due to the high water levels from that Mount Hope River at Warrenville. So if you want to go to the next slide. So here is a look at one of the main things from this event was a very heavy rainfall. You could see from northern Connecticut into parts of western Massachusetts. Again, similar color scale to what we had when we had Elsa go through, anywhere from roughly 3 to 5, if not some higher rainfall amounts. And actually, for some spots, the 3-hour average rainfall had up to 100 years return period, which is really, really high. So here's just a look at the surface analysis, again showing that we had a stalled frontal boundary, and you can kind of see that that's in one of those areas where that Mount Hope River in Warrenville, that's where some of the really heavy rainfall is. And this was actually a really classic setup where there was a stationary front, and then you'll see in a second here that we had some pretty good tropical moisture in place. So in that top left-hand corner, one of the things we typically look at is called precipitable water, and that's basically just a measure of how much moisture is in the atmosphere. And you could see at 6 p.m., which is roughly when the storms were going on, generally over southern New England, there were values around 2 inches. And then if you look at the sound and climatology for the Chatham upper air site, that's around 2 inches, which is just about at the max, if not really close to the maximum for July 17th. And then here is you can see on the bottom right-hand corner is that the rotation from the Somers, Connecticut tornado. You can see an image there. And then in the top left-hand corner, after the fact, when we get reports of damage, or if we have any strong rotation and and there's reports of damage in the area where we go out for storm surveys, you could see the storm survey for the Ef-0 tornado that happened with this. Moving on a little further into July, again, really busy month. On July 21st, we had a line of severe thunderstorms that produced pretty widespread wind damage across southern New England, and you could see below, as is kind of typically the case when we have these strong lines of storms go through, lots of tree damage down, and you can see those two images below showing some trees down. Here's a list of the storm reports across the area, and you can see that there's a large smattering of wind reports, and then just on the side there, you can see us cropped out what several of the reports and more of the specific details of the time, location, and then if there were any wind speed values associated with it. So here's just a quick radar loop showing the line of storms going through, along with the severe thunderstorm warnings and special marine warnings from 4 o'clock to 8 o'clock, and I'll let that go through one more time. So, and I know we go over it more in the 101, but there's a couple things when it comes to thunderstorms that are important. One of them is the surface instability, or in this case, we're looking at CAPE. And the higher the values are, the better the opportunity you have for stronger thunderstorms. And in this case, we had around 1,000, 1,500, which is not too bad as storms are starting to roll in through right before sunset. Another thing to point out here, it's not on the image, but you can kind of see the surface winds on there in the darker brown. And another important ingredient when it comes to thunderstorms is the amount of moisture. And typically when we have like a southwesterly or southerly flow, we're tapping into some better moisture, mainly due to the Atlantic, and or if there's more moisture coming in from the mid-Atlantic. And then the third important thing, aside from lift, is we need to have strong wind shear. And typically when you get around the 40 knot range, if you get it even higher than that, that increases the confidence of storms surviving as it gets through, provided there's enough instability. But if you have enough wind shear, that can help overcome the loss of instability, which is what we had in this case as the storms were moving eastward as the sun had set. So now getting into August, we'll talk about Tropical Storm Anri from the 22nd to the 23rd, and that's just an update from the Hurricane Center that they put out when the storm makes landfall, and in this case it made landfall along the coast of Rhode Island right near Westerly. So you can see here that there's the flight level winds that when they have the reconnaissance flights that go into the hurricanes, and I believe this is the one right around when they had made that they downgraded the Anri from a hurricane to a tropical storm. You can kind of see here the big thing was with the flight level, or the sea level pressure really goes down. But you could see as it get a little later on the 22nd that pressure had increased. And on top of that, usually those wind speeds, when the pressure's increasing, those wind speeds tend to not be as strong. And you can kind of see that there's an update from the Hurricane Center about what was happening at the 7 a.m. update when it was moving into southern New England. And then here's just a list of the damage reports across southern New England. You can see in although the colors are fairly close, the darker brown is where we have the tropical storm winds. The orange color is more flooding reports. And then the gray, I believe the gray would be either be the marine reports or if we had any coastal flooding. And then it's kind of hard to see because we don't have the track up, but we had a similar kind of situation as well. We talked about where the heaviest rainfall tends to fall on the left side or the western side of the track, and you could see all the heaviest rainfall over Connecticut and into western Massachusetts, whereas eastern Massachusetts, Cape Cod, and the islands didn't really get much in the way of rainfall. But then what happened actually with Anri as it moved in, you saw that it kind of moved in and then kind of did a left hook. Now the reason that that Anri took the path that it did is that it was being blocked by a ridge to the north over the northern New England, and because of that, that steered it into the eastern Great Lakes and actually allowed it to kind of hang around our area for a little bit. If you had remembered, if you remember late in August. And actually with Anri, and then before this, we also had Fred. We had a couple different tornadoes, several weak tornadoes due to the remnants of these tropical cyclones. You could see some of the damage photos in some of the images below, and then the Ingrid Landers. That's the tornado that went over Thompson Lake. And so you could see the Thompson, or it was Webster Lake, correction on that, Webster Lake. You can see the one that star is the Thompson, Connecticut to Webster, Massachusetts tornado. And this is from the August 19th. They were both Ef-0s, and again from the remnants of Tropical Storm Fred. And then also we had the Clinton, Massachusetts tornado. And then you can see here's our preliminary damage reports for both of those tornadoes. Again, both Ef-0s, with the Thompson to Webster tornado being a much longer path length than the brief Clinton, Mass tornado. And then just zooming a little more into the Clinton, Massachusetts tornado, you could see here, it was on the ground for about a minute, peak wind of about 80 miles an hour, a max path length of half a mile, and a max width of 35 yards. So, with this, you usually need some sort of forcing mechanism in combination with some of the other things we talked about. And you'll see potentially as a common theme here, we had a warm front over southern New England. And if you kind of get an idea of, if you kind of remember where those tornadoes were reported on the map, that warm front is pretty close to where those tornadoes were. And that's pretty important for helping these things spin up. So, and I think Rodney focused on it a little before, but you could see in the top images the 0 to 3 kilometer cape, the instability. As you get higher values, that gives a better potential for tornadoes. And then the below that, which is kind of an indication of low level shear, the 0 to 1 storm relative helicity. Once you get around the values of 100, that's pretty good, but if you keep getting higher, that really helps. And you could see the values once you get into that second line of blue, that's where we had above 100, which where those tornadoes were in that relative area. So just a quick radar loop, and then this is for the Thompson to Webster, Massachusetts tornado. You could see the rotation, and then the other thing to point out in it as well, as you can see in the correlation coefficient, one of the things we call the debris signature, and that's one way we can also confirm that a tornado was on the ground, but we do also still go out to do surveys to determine the rating, as you can't do that from radar imagery. And then this is another radar loop from a different tornado. This is the Stowe, in the Stowe area. Again, you can kind of see similar radar signatures where there's you can see the rotation and the storm relative motion, and along with and I don't think there was any debris signature on the correlation coefficient in this situation. And then in the bottom right-hand corner, another one we look at is the rotational. It's the rotation derived by GR analysts, and you can see as those values get higher, that's when you get more and more concerned about a tornado. And then here's some more damage reports. You've got the Marlborough, Massachusetts tornado. Again, all of these are Ef-0 and relatively weak in short length. The Bolton, Massachusetts tornado, and then lastly, the Stowe, Massachusetts tornado, which is what the radar image that we previously looked at was indicating. And then for this situation, again, another warm front helped focus the low level where we could spin up a potential tornado, and you can kind of see based on if you know the relative location of those locations, that warm front had lifted northward as time had gone on, and that helped things spin up. Now, again, looking at the 0 to 3 kilometer cape and vorticity, this is going through time through the day, and you could see here that instability is continuing to increase. And then because we had that tropical storm over us, that also helped in with the vorticity, which is basically the amount of spin, which really helped those storms get going. Moving on to our next tornado was the Dennis, Massachusetts tornado. This is around 1:30 in the morning. This is the public. This is one of the public information statements that we send out, and you can see that a weak tornado, again another Ef-0, had touched down early in the morning and lasts for less than a minute. And you could see a little more about the details of what kind of damage was reported as it went through. You know, again, noticing a theme here potentially. Another warm front over southern New England, again, has provided the focus needed for spinning up these tornadoes. And again, if you look at the warm front and the location of where the tornado happened, it makes sense. And then looking at some of the other things that we would look at, again, you have the 0 to 3 kilometer cape and surface vorticity. You can see that even though it's relatively low, it is impinging on an area where the front is located. We do have a good amount of low level spin with the 0 to 1 kilometer storm relative helicity. I want to say is in the 35 to 40 to 50 knot range there. Some really high effective shear. And then there is another thing that we have on the Storm Prediction Center's meso analysis page, which has indicates probabilities of Ef-0 plus tornadoes. And you can see as you look into southeast Massachusetts, Cape Cod, and the islands, that we're starting to get into some of those probabilities. So it's something if you see that, something to kind of perk your to keep an eye on. And then here's a radar loop of it. It's kind of hard to tell because I don't believe we put on the warnings, but you could see all the different thunderstorms that were going over the region. And you know, I know that we had the storm that had and I don't think we do a velocity loop here, but we did have the thunderstorm that produced a tornado out of that. There we go. Actually, here is the velocity loop. So you can see here a still image of the strong convergence south of Yarmouth Port at 1:15 in the morning, and along with a couple other images. And you can see the warning that we have in there as well. The other thing to point out is the rotational velocity. We've got 35 knot inbound and 35 knot outbound, showing there's some rotation there. Again, it's a relative. It's some good rotation, but given a tropical environment, that's a pretty good rotational signature, which leads to a 35 knot rotational velocity, which is one of the reasons that we had the warning out. And of course, we had the tornado in the Dennis area because of that. And then I believe at this point, I'm passing it along to Joe.
All right. Thanks, Bill. So I'm going to wrap it up with some of the fall and I guess just fall weather. We haven't had it. Today's the first day of winter. So late October, many of you remember the late October nor'easter. That was a surface low that really intensified pretty rapidly, brought high winds and tremendous number of power outages, especially to southeast Massachusetts. Some heavy rainfall and dangerous seas, and even some coastal erosion to southern New England. And I always like the picture on the lower right. The Coast Guard actually goes out and does training exercises during storms to help, during rough surf conditions. So that was a pretty cool picture that they shared with us. They were doing some training out of near the Merrimack River. So the surface analysis from this day, you can see the low starting off 10 p.m. Here on the left, and not moving too much. It's heading towards Nantucket by the early morning hours on the 27th, but it did drop 28 millibars in 24 hours, which is considered a bomb cyclone. I think many of you remember the January 2018 bomb cyclone that produced blizzard conditions and record coastal flooding in Boston. So if a storm drops at least 24 millibars in 24 hours, it's considered a bomb cyclone. So we certainly met that criteria. The lowest pressure was down to 976 millibars, which is 28.82 inches. And I think some of our stronger hurricanes actually are in that range. So this was certainly a very impressive storm. And again, a slow mover. Took its time heading toward Nantucket and then offshore. If you'll remember, the corridor of the strongest winds actually came in during the early morning hours on Wednesday. There was a core of winds here off the coast, which moved across southeast Massachusetts, Cape Cod, and the islands primarily. But it was about a 3 to 6 hour period of the highest wind gusts that really caused all the damage. And the power outages were extraordinarily high. In this case, about 500,000 in Massachusetts, mainly focused across areas south of Boston, the Cape Cod and the islands, with a secondary area around Gloucester and Cape Ann, which really outdid the number we saw in the October 2020 derecho. If you remember that, when we had a long line of storms crossing through the state and or the region, and that brought destructive winds 70 to 80 miles per hour in some cases. So certainly, a much more impactful storm, but over a much smaller area. One of the things that we were looking at that night were actually the wave heights. They got a little bit higher than we anticipated. We were thinking seas, 20, perhaps 25 feet, and that's usually where we start to see some issues with coastal erosion and coastal flooding. But in this case, the buoy here off of Gloucester reached a peak wave height of 32 feet during the morning on the 27th, which was really impressive, and that really led to greater coastal impacts than we had originally anticipated. And you can see here, this is in Sandwich, but actually during an hour before the afternoon high tide. So an hour, usually 2 hours before to 2 hours after is the main window for flooding. And you can see already quite a bit of water here around this parking lot an hour before the afternoon high tide. And even up on the North Shore, Newburyport, you can see, water has past these barricades that were put up 20 minutes after high tide. But even an hour after, there's still a lot of residual water left over that can't escape. And that usually will lead to more flooding on the subsequent high tides. So that's something we also watch for. And then going into November, we had our tornado outbreak, we're calling it. There were nearly a dozen tornadoes touched down on Long Island, Connecticut, and Rhode Island. And for Connecticut and Rhode Island, these were the first tornadoes on record in November, dating back to 1950. And if you remember from Rodney's April storm, there was also the earliest on record in Connecticut. So they had the earliest and the latest on record in Connecticut in the same year. These formed along a squall line, a line of thunderstorms, which didn't have a lot of instability, but a lot of shear, and that's caused by really strong jet stream winds. That's pretty typical for a late season outbreak in the fall. And as Rodney had with his April event, we also had snow falling across the higher elevations of western Mass, while tornado warnings were ongoing across Rhode Island and eastern Massachusetts. So I think many of you will remember that. And these were three of the tornadoes in our area, aside from Long Island, that occurred. The most significant being the Stonington, Connecticut to westerly Rhode Island. That was an EF1 with winds of 90 miles per hour. The other two, Plainfield to Foster, was an EF0 with 80 mile an hour per winds, as well as North Kingstown, Rhode Island. So relatively short-lived, 6 minutes here, maybe a little more than 10 minutes here. Very typical for our tornadoes, and mostly tree damage in these cases. So Bill was kind enough to generate this nice radar loop for us, which shows the line of storms moving through southern New England, along with some of the warnings, the tornado warnings in red, severe thunderstorm warnings in yellow, and special marine warnings for the waters in blue. You can see a line lifts up across the area. And the thing to note is you've got a lot of little kinks in the line and buckles in the line, and that's really where these tornadoes tend to form. They're very short-lived. It makes warning very challenging as far as tornado warning. So really, what we try to do is issue a severe thunderstorm warning for the line and mention possible tornadoes because they're so brief and they, maybe a minute or two at most. But if we see a better circulation, we do try and issue a tornado warning for that, especially for the stronger storms, the EF1s and greater. So what was happening that day? We had a pretty sharp, what's called a trough or dip, kind of in the jet stream here across the Northeast, and a really strong core of winds around it. You can see ahead of it, you've got some. You see all these flags here. These are winds in excess of 100 knots, or 110, 120 miles per hour here off the coast, which provide added energy, the added wind shear that we talked about. And this pattern is actually pretty favorable from our tornado study that we've done. This is a type B, which is kind of the second most common, the most common being that closed low kind of over the Great Lakes or nearby. But it's these troughs swinging through, especially late in the season, that can really cause some, a good severe weather outbreak or even tornadoes. And in this case, looking at the station plot, we have our warm front nearby and our cold front, but there's actually this weak low. We call it a mesolow because it's on a small scale. And you can see you've got southeast winds ahead of it. You've got kind of northerly winds behind it and southerly winds in this warm sector between the two fronts. And you can see it's 58 at Block Island with a dew point of 50. So that's some unstable air that was moving up as this low came through. And this low actually gives you that added spin right at the low levels and helps spin up these tornadoes kind of from the ground up. They're not the classic tornadoes that we see in the Midwest that form aloft and work their way down. These form from the ground and work their way up, almost the exact opposite. So whenever you have one of these little mesolows or warm fronts nearby, that's something that we always need to watch out for, is the tornado potential, especially in kind of a moist environment like this, even though temperatures were only in the 50s. And again, along with some of the other tornadoes we looked at, we've got this co-location of the instability or cape in the red and the vorticity or spin in the blue. And no doubt it's right over, Long Island, Connecticut by later in the day. And this is the area where we had the tornadoes form. They didn't really make it much inland from the coast. And we also think on a side note that the warmer sea surface temperatures also played a role in providing some added instability for these storms to develop. So definitely an interesting late season event from there. So with that was a look at our top events of 2021. And at this point, I think I will have Rodney and Bill come back and we'll go through some questions. I know Bill is answering some in the chat because we have quite a few, but let's go through and see what we can find. So let's see. Okay, from Richard, here's a question about snow forecasting. And you might want to check out our Winter Weather 101 and especially 202 on YouTube because we get into this a little bit more. But he wants to know if we can explain the relationship of the 540 line, that's a thickness line, with forecasting snowfall at the surface. Bill, I'm going to hand that to you since you answered that in the chat, but that's a good question for everybody.
Yeah, so just to give everyone so that there's a lot of things that go on with forecasting snowfall, but in this case, the 540 line, it's a difference between 1,000 millibars and 500 millibars. It's just a difference in height. And when you do that difference, usually there's a value that's called 540 or 5,400 meters. And that roughly follows where the surface temperature is freezing. So if you've got values that are below 540, that typically indicates that there's going to be snowfall. And then if you have values above 540, that indicates rainfall. Now, there's a lot more that goes on. It's a fairly simplistic method that we do still look at. But there's a lot more that can go on between 1,000 and 500 millibars. So there's a lot more you got to look at, and little subtle differences in temperature can make a big difference in precipitation type.
All right, thanks, Bill. And yeah, we usually kind of use that as a first look just to kind of get a general idea of where the rain snow line is. But we start to look a little more detail at the lower levels, things like temperatures, like that 2,500 foot level to kind of really determine it. But out, a few days in advance, it's a good kind of first guess as to where the rain snow line will be. Next question from Kevin. Did the instability gradient play a role in forecasting severe storms during the summer? And I'd say, Kevin, yes. We don't always look at the kind of the max value or where that maximum value is. What we kind of look at is the gradient. And you notice, especially with the Cape Cod tornado, that formed right on the edge of that instability. So a lot of times gradients are just as important as the actual values. If you've got a warm front nearby and you're on the edge of the instability gradient, that's a favorable area. So good catch. You've been paying attention, Kevin. A+ for today. And we talk about that a little bit more in our Severe Weather 202 webinar, if you want to take a look at that for some severe weather forecasting. Comment from Sebastian, or question, weren't there some pretty significant waterspouts offshore of southern New England with the remnants of Ida as well? And I know Bill answered that, but yeah, there were. The problem is we don't always get ground truth that they're occurring because the vessels tend to avoid those areas when a special marine warning goes out. But based upon what we see on the radar, the rotation, you don't always see it drop in the CC with the water. But yeah, it's probably a good bet there were a number of water spouts there we just didn't know about. So good point. Let's see. From Kevin, does DBZ, the reflectivity, help forecasters measure the intensity of storm motion, but correlation coefficient differences from raindrops and non-meteorological objects? So, Kevin, reflectivity is a measure of the signal that's returned. So think higher reflectivity means essentially heavier rain or even heavier snow, like Rodney showed with the February 7th storm. The storm motion is more in that velocity that we showed. And the correlation coefficient, yes, it kind of tells us the uniformity of the drops or whatever it's detecting. So if it's up near 1, which is kind of that purple shading, everything's uniform. So it could be raindrops, snow, snowflakes, things like that. When it gets lower, then there's kind of different things going on. Sometimes it's birds. Sometimes it's insects. Other times it's debris, like leaves and branches from tornadoes. So that's kind of how we use those different things. Let's see, Rodney, we got one for you here. Any advice for high schoolers planning on going to college to study meteorology? This is from William. He's planning on studying at UMass Lowell, majoring in atmospheric sciences. But is there anything else that helps?
Yeah, thank you, William. That's a great question. I think, speaking personally from myself, it's never too late to be to want to become a meteorologist. But it's also great that you at a young age you have this clear vision of what you want to do. And I would say just the main thing is to stay curious and stay humble. There's always something to learn from every day, and just know that it's going to be a path that is full of adversity and difficulties. Because a lot of people going into meteorology school, I mean, a lot of them have the passion, but there's also a lot of math and physics to go through. So be prepared to put in a lot of hard work. When you get to college, just be prepared to put in a lot of effort, but at the same time also enjoy. It's because your passion is going to help you through the difficult times, and also you also have your friends and classmates to, if you think it's difficult, they would also think it's difficult, but teamwork can go a long way to help you navigate meteorology school. So I think in a nutshell, I think I'm excited that you are thinking of a path in meteorology, and I think I highly encourage anyone with interest in weather to pursue meteorology, but just bear in mind it's not going to be easy, but doable if you have the determination and if you're willing to work together as a team. So that's my 2 cents.
Yeah, great advice, Rodney. I mean, I for one was loved the forecasting aspect, and when I got to college, it was wow, this is a lot of math and a lot of physics and chemistry, and you get yourself through it. You don't have to be an expert and get all straight A's, but you have to get through it, and that's where you have, like Rodney said, friends, classmates, you do study groups, things like that, you'll get through it. So don't let that squash your enthusiasm. If you have a love for meteorology, which it sounds like you do, William, go for it. And, don't hesitate to contact any one of us for any advice. So you have my email address there, or, I can put you in touch with Rodney or Bill or anyone else at the office to help out too. So get involved with different things. UMass Lowell has a great program. We have student volunteers there outside of the pandemic to work with us too. So best of luck, and let us know how things are going down there when you start. I'm sure you'll do well. From Bill, question, I'll hand this one over to our Bill. Do you use drones when evaluating tornado damage? That's a good question.
Yeah, I know at least on the surveys that we've been on, our office does not have a drone. That doesn't mean if someone passes along drone footage to us that we wouldn't use it, but I know that there are other offices that have used drones when trying to determine tornado damage.
Yeah, and we also have help from our media TV meteorologist partners. A lot of the TV stations have drones. So they'll share their footage with us. Also, actually, I think some of our amateur radio folks have drones too, so we get that through our Skywarn network. But yeah, we do. It's always a great help, especially for surveying areas that we can't necessarily reach by foot, which I believe, Bill, happened a couple of times this past year. We actually used drone footage to help out with some of the paths.
Yeah, I think the Thompson tornado, because we couldn't get to some of the damage. I believe we got some drone footage from the folks in Connecticut, and that was really, really useful.
Yeah. So yeah, definitely, a new piece of technology to help us, better document these tornado tracks. So good question. From Ronald, and Bill, this was in your section, so I'll give it to you. Was Tropical Storm Anri considered an oddball tropical system event for our area since it formed so far north of the tropics, then was pulled in?
I'd say it was definitely not like the typical path that we tend to see when we get tropical systems. So I mean, it's definitely not a typical path. I don't know if I call it an oddball system because it's still the time of year that we can get tropical weather. But definitely not the typical path that we see when we do get tropical systems.
Yeah, and not all systems form way out over the Atlantic and take days to come across and then move up the coast. Some of them were more what we call homegrown systems. Sometimes that form in the Bahamas, which is what we always want everyone to pay attention to. But sometimes even off the Carolinas, you can have a system form and then very quickly and then kind of move up into our area. So, in that sense, yeah, we don't see too many form north of the tropics. As opposed to the big buzzsaws that come roaring across the Atlantic for days or weeks at a time. Let's see, from Sebastian, a winter weather question about snow bands. Rodney, I'll toss this to you. Is analyzing frontogenesis and thermal gradients the prime way to forecast strong snow bands, or are there other ways commonly used as well? That's a good question.
Yeah, thanks, Joe. Yeah, that's a great question. I would say that using frontogenesis at 700 millibar, and I mean, in fact, really, if you look at 925 to 700, that is where, you have ice crystals form, and, where you can form the dendritic snow, what we call the dendritic growth zone. So I would say that the frontogenesis is a key ingredient for manufacturing snow and getting significant heavier snowfall rates. But it's not it's not all inclusive. So you do have to look at there are also other ingredients like, for example, start off at the synoptic level, at the bigger scale. Ideally, you should have like a strong high pressure system that is set up, in Quebec, and because you need cold, dry air to be in place, because otherwise, when you have a warm front lifting north, you're just going to change over the precip very quickly, like for instance, like the storm that we just had, very quickly changed over to sleet and freezing rain, just because we do not have cold enough air in place. So I would say, besides the frontogenesis, you can have all the lift you have in the world, but if your air mass is not cold enough, you're not going to get snow. So ideally, you want, again, cold, dry air in place. Have the injection of fresh, cold air mass, and then you have the warm front lifting off. The track of the low pressure is important too, because ideally you want it to be where we call the benchmark, the 70-40 benchmark, 70-degree west, 40-degree north benchmark. If the low pressure tracks inside the benchmark, say maybe closer to Nantucket, then you have to worry about, the I-95 corridor probably going to change over to sleet and rain. But if it's too far offshore, it's southeast of the benchmark, then you might not get anything other than a few cold, snow showers. So, I would say, boil it down to, at least in my opinion, 3 ingredients. So you want cold, dry air mass in place with a high pressure and the right storm track, and then add to that the frontogenesis, where you can set up 1 inch to 2 inch per hour snowfall band. So, I hope that answers at least part of your question.
Yeah, good answer, Rodney. And I think you showed it in the February 7th storm. Remember, we almost always see 2 different bands of, maximum of snowfall. One is with that 700 millibar, or like roughly 10,000 foot frontogenesis. That's called the mid-level band, and that's usually just northwest of that frontogenesis max that you showed, Rodney. And then there's a lower level band, usually around that 2,500 foot level, which is the thermal gradient, which you showed near Nantucket. So that was a classic example, that February 7th storm, of having those 2 bands kind of in our area. Sometimes, the mid-level band ends up going out near Albany, or even, way into upstate New York, and we don't get left with too much, and we get the lower level band with the coastal front. So those are 2 things to look at, Sebastian: the mid-level and then the lower level as well. So good answer, Rodney. Thanks. Paul just wanted to know if we discussed the Ida flooding. We didn't discuss the flooding in New York City with that. We were kind of focusing just on southern New England, but certainly there was obviously, deadly flooding that occurred in New York City with the remnants of Ida. We didn't have quite the same impacts here, but we discussed the tornado that was on Cape Cod from us. We did have some flooding, but not to the extent of New York City, Paul. I believe the New York City office does have a review of that on their webpage. You may have to hunt around, but if you can't find it, just shoot me an email and I can point you in the right direction. And Ronald wants to know, just a couple more questions here and we'll get to the weather briefing. Ronald wants to know, speaking of drones, is it possible to use a heavily armored drone with sensors that would get pulled into the tornado to obtain readings? Or is he still stuck in the Twister movie mode? Yeah, I would say it's more Twister movie mode, Ronald. I don't think a drone would, even if it was heavily armored, would be able to fly in a tornado, or let alone probably survive one. But we never know. Maybe down the road someone will create something for that. And from Sebastian, one last question. Rodney, this is a snow one. Do the 30 to 40 dBz reflectivity values typically correlate well with 3 to 4 inch snowfall rates, or per hour snowfall rates?
That's the best, and that's a great question. So, I would say you need to use the reflectivity product alongside with the correlation coefficient product, because sometimes, when you get mixed precipitation, like sleet, snow, raindrops, you can get pretty high reflectivity, and that's what sometimes we call bright banding, and it might be tempting to think that's a heavy snow, but that might actually be heavy mixed precipitation. So there's a lot of junk involved in it. So, and when you take a look at the correlation coefficient, it really sheds a lot of light on what kind of things you're seeing, because correlation coefficient, it has it's on a scale of 0 to 1. So if everything is uniform, it's all snow, you should get a correlation coefficient pretty close to 1 because it's uniform precipitation. But if you get a mixed precipitation, you start seeing lower values like 0.9, sometimes even 0.8 if it's mixed in with hail. And so, back to answering your question, so if you see 30 to 40 dBz reflectivity, you would have to compare it with correlation coefficient to see if there's actually a uniform type of precipitation. So it might not be all snow, it might just be a mixed precipitation.
Yeah, good point, Rodney. And yeah, if it is all snow, you kind of have to know the environment, which, most of us track. So like in that February 7th storm, we knew it was all snow, so it was coming down pretty hard, but also the temperature. If I've seen, cases near the Great Lakes or even, Cape Cod with ocean effect, if we have an Arctic air mass in place, sometimes it's snowing 3 to 4 inches an hour with 20 dBz, believe it or not, because it's so cold. So it also depends a little bit on the type of the air mass that's present. But in general, yeah, I think you're right, Sebastian. If you're seeing, 35, 40 dBz and it's an all snow situation, it's snowing pretty darn hard. So hopefully there's someone down to, measure and actually confirm what you're seeing on the radar. So that's really good. Okay. So from there, we're going to end the questions here, but if you have anything, feel free to throw something in the chat as we go along.